Hey, Cody.
Hey, Brock.
So I was thinking about our physics class today, and my teacher, I don't know what she was thinking, but she was thinking that a ball could move a door farther than clay. If the clay sticks to the door, wouldn't it move it farther?
Actually not. That's a common misconception.
What? There's no way.
Yeah, and there's actually a way we could prove that with the materials you have in your hand.
Really?
Yeah, we could design an experiment.
Wait, Cody. Hey, Cody.
Oh, hey, Brock. What's up?
But wait, Miss Bennell said that there was a door involved. What are we going to do differently with this?
I was actually thinking about that. We would want to simulate that experiment to the best of our abilities, but one thing you have to take into consideration is we have a small ball of clay, correct?
Yep.
And a tennis ball.
Okay.
Okay? That clay has a mass of about 2 grams or so. If we take the door into account, it's going to have a huge mass. So that ball, both balls, whether it's elastic or inelastic, both aren't going to have much effect on that door when we try to hit it. So when you have something like a skateboard with smaller mass, that mass of the clay or the ball is not going to be negligible, and it'll actually move it and give us more accurate, measurable results.
Oh, thanks, Cody. That makes a lot of sense.
Yeah, of course. All right, Brock. So here's what we're going to want to do. First, you're going to have to obtain your materials. This is going to require that skateboard, that lacrosse ball, a measuring device, and of course a lot of duct tape, and I do mean a lot of it. First, what you want to do is you're going to build this contraption with the open face of the cup facing towards the ball where you're going to throw it. And the way you're going to do that is you're going to duct tape around the cup so that it faces, and you're going to need to take into account that the ball is probably going to bounce out when it hits the back of that cup. So you might want some tissue paper at the end to cushion its collision so that we can have more accurate results. And you're going to do 3 trials of that, and you're going to want to make sure to mark it. Another thing you should keep in mind is that you have a level playing field. A lot of times this could alter your results and offer some confounding variables. So like I said, you're going to do 3 trials of that, and you're going to want to do your best to keep those throws consistent. And the way you do that is just try to swing your arm in the same exact motion each time. Unfortunately, due to a lack of resources, we can't be completely controlled, but we can do our best, and the results should still be substantial enough to make conclusions. Finally, on your last step to simulate the elastic collision, you're going to remake it with the closed face pointing towards the ball throw. And you're just going to take that duct tape and you're going to switch it around towards the other end, and again do 3 trials and measure. And finally, when that's done, you're going to compare your results, and regardless of your source of error, hopefully our hypothesis should be true and the elastic result will carry the ball further. Oh, hey kids. Today we're going to be working on measuring the difference between an elastic collision and an inelastic collision by throwing a lacrosse ball at this board and seeing which one goes further in the 2 different types of collision. Obviously, this experience has several different points of hazard. So one of the things you guys want to remember about experimenting is doing it in a safe and proper way. So we've got all of our gear here. First thing you're going to want is eye protection, all right? Flying lacrosse balls have taken a lot of victims this past year. To make sure everything is nice and clear, get your handy headlamp. Okay, and just to make sure no explosions in momentum jar your head, you're gonna want your ear protection. And of course, in case the friction gets too hot, you're gonna want some gloves for heat protection. All right, and without further ado, we're ready to get to physics. Go with the front of the wheel here. We're just going to go ahead and make our tick mark right there. And looks like that's approaching right at 18 inches, and that was our inelastic collision. Inelastic collision, trial 2. Inelastic, trial 3. Alright, so one of the confounding variables of this contraption here is that the ball would hit about right here and then, thank you, the ball would hit right here and then hit right here and therefore slow down its velocity and thus create a smaller momentum. So what we're going to do to fix this is we're going to just move this cup back. I can't stop. Elastic collision, trial 1. Alright. Elastic, trial 2. Final trial. Hey, so as you can see from our 6 trials comparing elastic and inelastic collisions pertaining to momentum, our inelastic collisions range from about 18 inches to about 22 inches, whereas our elastic collisions range from about 28 inches to 29 inches. Some of our sources of error were a lack of resources. We weren't able to get the velocity exactly right, but despite that, the laws of physics still applied, obviously, because the elastic collisions went further.